in the former slide were people from the event horizon. Can you hear me well, by the way?
Yeah.
Okay. So these are people from the Event Horizon Telescope collaboration, which is also centered here in Harvard, so that we could speak a lot to them. And after the image came out, they really kept the secret very well. We didn't see the image before it was published, and the minute it was published, we were kind of staring at it for many, many hours, at this orange donut, and trying to understand what are we actually seeing here. So together with them, and also many hours alone, and it's really, so the current resolution of the image, I mean, will get, we hope, better. I mean, it's still quite amazing that you can see the shadow in the middle. For me, it's still quite amazing, but the current resolution is about this, the length scale of the width of the donut, you can say. That's, I mean, that's so kind of this width. So it's still, I mean, the only really features that we can really recognize here in the image are the fact that there's a shadow in the middle, and it's significantly, so it's 10 times less brighter in the middle. So there significantly is some shadow there. And also this brightness asymmetry in the bottom side, image is about 3 or 4 times more bright than on the upper side of the donut. And that's what we were trying to understand in the beginning. So there are several effects that contribute to this brightness asymmetry. One is the Doppler shift, because so even if this black hole, for example, is not rotating, the accretion disk is rotating around the black hole. And so on one side, the accretion disk is coming towards us, and on the other side, it's going away from us. And then there will be a blue shift on one side and red shift on the other side. This is one effect. But then when we started thinking about it, there's another effect that that also contributes to that, and that is related to the so-called photon ring, which will be my main focus today. So in the end, we realized that describing the brightness asymmetry is not very simple, and we were kind of hoping that maybe we can say something just from general relativity about what should be the prediction about this the brightness asymmetry. But it turns out that this also depends a lot on the details of the accretion disk. But what we did understand during thinking about this is some details of the so-called photon ring, which do depend only on the Kerr metric. And that's what we were trying to kind of, the main idea of this work was kind of trying to isolate what depends only on the geometry, on space-time geometry, Kerr geometry, which is very simple. Depends only on 2 parameters, the mass and the spin of the black hole, and what depends a lot on the details of the accretion disk, and how can we kind of isolate these two characteristics of the disk.
Oh, Shahar, in this
so
image,
of course, just yeah.
In this image that we're seeing, are we seeing the
Yes.
photon ring or the accretion disk?
Great. So this is exactly what I will start analyzing in more detail. I can spoil it now. I mean, we're seeing both. We're seeing both, but we don't have enough resolution to see the photon ring yet. The thing is that flux-wise, it is the direct image that's contributing about 90%. But about 10% of the brightness that you see here is the photon ring, but it's kind of smeared into the direct part. Yeah. Okay, this is of course this black hole is a black hole in the galaxy M87 that famously was appeared on the first image of the Event Horizon Telescope a year ago. This black hole is about the size of the solar system. the Schwarzschild radius is of the scale of the solar system. It's a huge black hole, one of the hugest that we know of. Okay, so this kind of turned, so looking at this picture, staring at it for, oops, why, for some reason, wait, you still see the picture?
I still see first image of a black hole M87.
Interesting. Why is it not updating? Huh. Why is this?
It's moving on your screen?
Yeah. Should I stop share and share again?
Yeah,
Something?
let's try that.
Okay. Sorry. Okay.
Now I see a black screen.
Okay. Good.
Okay. Now I see something different.
Great. Okay. All right. Okay, so yeah, just I forgot to say that this black hole is about 60 million light years away. Okay, it's outside of our galaxy. It's 60 million light years away, and it's about 6 billion solar masses. So that's the mass that corresponds to the this Schwarzschild radius size of the scale of the solar system. And the inclination angle, if you're asking yourself, I mean, what kind of angle are we looking at this thing from? So we're looking at about 17 degrees from the axis. Oh, sorry. So we're looking at about 17 degrees from the axis, and the projection of the spin axis is to the left. It's to the left in the image that you're seeing now. So that's kind of why. Okay, so try to, we're looking at it from, like, the spin axis is pointing away from us and a bit to the left. So that's why the bottom side is coming toward us. Let me actually, do you see my screen, my blackboard here?
We see the board, but I'm not sure what resolution we'll have if you draw on it.
Too small.
Probably too small, Shahar.
Can you double click on my image to see it? Well, okay, otherwise I can actually draw on my iPad.
That probably will be better on the iPad.
No problem. I can actually draw on the image. Okay, good. So what am I saying here? I'm saying that the spin axis is kind of into the board like this and a bit to the left. All right. We're looking from down. And so the thing is all rotating like this. That's why the top part is going away from us. The bottom part is going toward us, but only like a small projection of it. It's mainly just we're looking from below, 17 degrees off the axis. Okay, just to, and still we have this brightness enhancement of a factor of 3 or 4. So this kind of tells us the velocities are very relativistic, even though it's just a small projection, but already like such a big difference in the redshift, blue shift. All right. Yeah, please do stop me whenever you want, whenever you feel like it. Okay. So this led us to, okay, so this is the realistic image that we currently have. I think it's quite amazing that we have it already. I would love to have more resolution, of course, but it's already quite amazing what the Event Horizon Telescope did, in my opinion. And I think it can improve a lot. So we were trying to understand kind of ideally, what should a black hole look like if we had infinite resolution? And this answer turns out to be quite complicated. It depends both on astrophysics of the accretion disk and of general relativity on the metric. And as I told you, we were trying to kind of isolate these two factors. So this question, what does a black hole look like, ideally was studied for many years already. It was pioneered in the 70s by Bardeen and Luminet. But I think that now, when we really have an image to look at, I mean, we're starting to realize what we really need to understand about this, that will really connect us to the real world and to the observations. So these are, so here these 4 pictures are simulations of what the black hole in M87 should look like if it's really inclined 17 degrees with respect to us. And these are results of a GRM-HD simulation, so a GR magnetohydrodynamic simulation, which is a very costly, very heavy simulation of the accretion disk physics in the curved background of the black hole. And to generate the images, you do a numerical ray tracing, which I will describe in a bit. So you kind of, okay, first you do, this was done, these are simulations done by the Event Horizon Telescope collaboration. This simulation of the GRM HD of the accretion disk, and then they ray trace back to the screen of an observer far away, and then they get all these nice images. These are images that correspond, of course, we do not know what the spin is, but this is for a choice of spin of 0.94 out of the maximum is 1, maximally rotating black hole is 1, A equals 1, and from an observer angle of 17 degrees. And as you can see, and and what is different between these 4 images? So what is different is these parameters, sane or mad, as you can see, and R high equals 10 or equals 160. These parameters, mad or sane, correspond to are related to the magnetic fields in the accretion disks, which actually generate the radiation. So they relate radiation is generated via synchrotron radiation. And this parameter R high is related to the temperature difference, some parameters of the density of the electrons in the plasma. Okay, so these parameters are really different parameters in the accretion disk. We don't know what their values are. And in principle, what you need to do, if you don't know, is you generate many images for many different values of these parameters. And then you try to compare the images to what you actually see. But if you look at many different images of the black hole that were generated in many different numerical simulations generated by the Event Horizon Telescope, you see that there are many differences, as you can see, but there are also many similarities. There are many features that are universal. So one thing you can see is the shadow in the middle. And another thing you can see is a bright ring of enhanced brightness. As you can see this bright ring in all the different images. And it kind of looks the same, right? I mean, and kind of seems like it doesn't depend on the details of the accretion disk. So this will be the part that's more related to general relativity, and that's the part that we try to understand in this work. Okay, so
ask a question.
Yeah,
sure. How well do you know the spin of this black hole?
We don't know it at all. I think, I mean, currently the mass is there's a pretty good estimate of the mass. We think it's about 6 billion solar masses, but the spin, really don't know. The only indication that we do have is that, I mean, at least the only guess is that it's above 0.7 m.
Because you'll have
that's what people think. sorry, because there's a jet.
Yeah, but you have a very strong dependence of the shape that you're seeing of the ring on the spin.
Right. So exactly. So I think if we can see the ring, we will be able to know more on the spin. Yes, definitely. But currently, all this ring is blurred into in the image that currently we have. It's all blurred into the. So you see this ring feature is. This ring feature is kind of blurred into the rest of the accretion disk, which is less bright but contributes the most of the flux. So this all is kind of blurred one to another. So currently we don't see the ring. If we could see the ring, I think that we could definitely say something about this thing. Okay, great. So again, we're looking at this. Oh, good. So we're looking at this picture of the, again, a simulated picture of the black hole in M87. I mean, or the if it would have 0.94 spin, and so again, you can see here that the image is kind of, you can separate it into two parts: a direct image. So, oops. Now we can see better, right? A direct image, which is all the accretion disk, all this blurry cloud kind of around the shadow, and a very bright ring that has only about 10% of the flux. Whoa. That has only about 10% of the flux. Okay, this I explained, I think. Okay, and how, okay, good. So let's say that in these simulations, let's say that we already did the GRM HD simulation. Now we want to generate the image of the black hole. How do you compute what the image of the black hole should be like? You take a screen very far away from the image, from the object that you want to image, and then you shoot light rays in your simulation. I mean, this is just, I'm explaining now, how do we compute an image of any object? Doesn't really have to be a black hole. You shoot null geodesics. This is this blue line here. Back from the image, from any point of the image, you shoot them back. And they go through the accretion disk. They go through regions which are emitting light. And then you just need to kind of count how many photons are emitted along the null geodesic. Sorry, I didn't see the questions in the chat.
It's okay, I got those covered. When there's something that you need to answer, I'll raise it.
Okay, but feel free to stop me at any time, please. Okay. Good. So this is all this process is captured by this equation down here, which is called the radiative transfer equation. So I is the brightness that we see at the point on the screen, and to compute this brightness, we need to integrate along this null geodesic, and at every point we need to add the kind of emissivity J, and subtract how much is absorbed, which is itself proportional to the brightness. So to the number of photons already on the ray. But let's, for simplicity today, assume that we're in an optically thin scenario. So let's just forget about absorption for now, okay, for simplicity. So we just need, it's a very simple equation. We just need to go along the null geodesic and integrate all the regions which are emitting photon and count how many times photons are emitted. So basically proportional to the so-called emissivity of the region, J. Okay. And they didn't say that as you go along, as you go along the screen over here, kind of shooting null geodesics at different angles on the screen corresponds to throwing back null geodesics with different impact parameters. towards the black hole. It's kind of changing the conserved momenta, the angular momenta. When I shoot back null geodesics at different points of the screen, I'm shooting them actually with different impact parameters, which correspond to different angular moment for this null geodesic or light ray. Okay, good. So from this, we understand that in order to understand the image of the black hole, we need to understand light propagation or light ray propagation in the black hole geometry. So let's remind ourselves how this happens in a Schwarzschild, in a non-rotating black hole. So in a non-rotating black hole, we have the following. We have these conserved quantities, which are the E, the energy, and L, the angular momentum. Conserved because they're a spherical symmetry. And this geodesic equation, the geodesic equation, which can be written like this, can be reduced to a one-dimensional problem, which is effectively a motion in some potential big R. Okay, so you can think of this big R as a potential, actually as the total energy minus a potential. And this is a kinetic energy term. And sigma is the affine parameter along the light ray. So all this story is reduced to a motion in a one-dimensional effective potential. One-dimensional motion and effective potential, R. And you can think about this R as kind of a E minus V. Where V is the potential energy and E is the total energy. In other words, this equation tells us total energy equals kinetic energy plus potential energy. Okay, you do this reduction using these conserved quantities E and L. Okay, and in Schwarzschild, for non-rotating black holes, this will be the form of this potential. Very simple. With rho, so m is the mass of the black hole, r is the radial coordinate in the black hole geometry, and rho is the angular momentum over the energy. So it's the impact parameter. Okay, this is again a graphic illustration of this thing. So as you can see, that this is our one-dimensional problem of motion and a potential. So we have the total energy is always 1. Okay, because you saw that this R is just 1 minus this thing. This thing is the potential, and this thing is the total energy. Right? So we have energy 1, and this will be the potential. It depends on this parameter rho. So if we throw, let's say, if the impact parameter is large, then the potential, the peak of the potential will be above the value 1. And then if we throw a photon from, oops, and then if we throw a photon inside, it will hit the potential and bounce back to infinity. Okay? But if our impact parameter is small enough, the peak of the potential will be like this, below the value of the kinetic energy, and then if we throw a photon, it will just fall into the black hole. Okay, that's basically the picture in this one-dimensional reduction. Now, of course, there will be the case where we're exactly at the rho has exactly the value, such that the potential exactly grazes kind of this value of the total energy. And that will be the critical case. And there will be a certain critical radius, R critical, okay, in which the potential, or this total energy minus the potential and the derivative of the potential is 0. And this is exactly what determines the so-called photon sphere. Oops. Which happens at r critical equals 3m and rho critical equals 3 square root 3 times m for a non-rotating black hole. It's independent of the angle. It depends only on the impact parameter. So, okay, but in order to understand now, we can ask, okay, so at what happens at this critical radius? You throw a photon exactly with that critical parameter, and it comes in from infinity, and then it stays actually forever. It comes exactly with the right impact parameter, so that it stays near the peak of the potential forever. But it's of course, it's an unstable point. So it can stay near the peak of the potential forever, but this is like a mathematical idealization. So let's be interested in something more physical. Let's be interested in the near critical orbit. We can expand near that critical parameter and near that critical radius, and define these delta r and delta rho, which are r minus r critical and rho minus rho critical. These guys over here. So this will allow us to analyze what happens when we shoot with near critical parameters, what happens near the peak of the potential, and near that point, the radial potential looks.
Is this going to be some Lyapunov expansion?
Yeah, yes, indeed. I mean, this will come in the maybe the next or the slide after that. So yes, indeed. Yeah, so near the top of this potential, near the top of the of the potential, this function r assumes this very simple value. It's just a quadratic in delta r and linear in delta rho. Right, so you can do an expansion near this surface of near rho critical, and for example, we can calculate the total azimuthal angle that the photon traverses around the black hole as a function of the deviation from the critical from rho critical. So as a function of delta rho. And why are we calculating this total azimuthal angle traverse? Because this tells us kind of how many times the photon goes around the black hole. It's not a discrete, it's a continuous parameter, but if I just shoot it very far away from the black hole, it will just traverse an angle of pi. But if I shoot it very close to the black hole, it could start traversing more angle. And then this tells us how many photons it picked up as it goes around the black hole, because as this analogy, as it goes around the black hole, it picks up more and more times. It can pick up more and more photons. And this is what's responsible for the brightness enhancement near the photon ring. So this delta phi is just this integral over the total affine parameter, integral d. What's happening here? Right, and then we can substitute from the geodesic equation this form that I showed you earlier. And I mean, the details are not super important, but the thing is that there's a logarithmic divergence as we decrease delta rho, as we go closer and closer to the critical impact parameter. So delta rho goes to 0, and we get this log of some cutoff. This cutoff is kind of depends on when we're entering the region of near criticality. It's just some number. Okay, this is just some number, and it's some finite number over 0. So it diverges when we're very close to the critical surface. And this was analyzed already in the 80s by Ohanian. Here you can see this plot. So this is exactly what we're plotting. It's phi, basically some angle as a function of the critical parameter, and you can see this divergence as you go close to the critical rho. But it's a very mild divergence. It's a logarithmic divergence. So if, for example,
we have a question. We have a question from Yehu. Yehu, would you like to audibly ask your question?
Hi. Yeah. Shouldn't we
Oh,
see?
sorry.
Hi. Shouldn't we only see
Hi.
a shadow? I mean, beyond the photosphere?
Um, you mean for on the screen, if
For
I go
the
farther
picture.
away from the right. So let's go back. Actually, I think it's stuck again.
It might be because we didn't see the last things you were writing on the screen either.
Oh man. Oh, sorry. Okay. Okay. Yeah. Yeah. Now I'm realizing this only now. Let's do it again. Okay. Okay. No problem. I don't know why it's doing this. Hmm. Okay.
So we see, okay, now we see something.
All right.
Oh, great.
Okay. Let's go, for example, actually to the, you see this?
We
Yeah.
see the universal signatures of the photon ring.
Yeah, I'm going back to the simulated image that I showed here. I think you can see it very well here. So this is the critical. So the critical impact parameter is exactly where you see this brightness enhancement, this divergence of brightness. This logarithmic divergence is what you see here, where the brightness grows very large. But you can see that you do see some emission on both sides of the surface. It doesn't have to be zero outside, actually. It doesn't have to be zero outside, and I will explain this more. So it's kind of it's super confusing. You can get brightness inside the shadow. You can, I mean, if you think of the shadow as what's inside this critical surface, you can. This is sometimes called the black hole shadow. Because why it's called the black hole shadow? Because if you shoot geodesics from infinity, and you stand on the other side of the black hole, you won't see anything inside this shadow. But if you have emission close to the black hole, like an accretion disk, then you can see things both inside and outside, in principle. But you will see an enhancement on this critical surface, as you can see here. So it's, yeah, it's,
Just to make sure.
so that's, I think,
Shahar, just
my
make sure I
answer to you.
understand.
Yes.
If photons come from infinity, and they have some impact parameter, but they're basically traveling at parallel to the line of sight, then those light rays will be trapped inwards. But if you have something coming from around the black hole, it can actually have a wider angle and be strongly deflected, but still reach the observer, which is why you can see stuff from within the light ring, right?
Yes. Yes, exactly. 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 So, okay, let me, what did I also want to say? So about, can you see now this was the slide that I was talking about, the thing that you didn't see.
Yeah, so now we see a deflection angle as an integral over the affine parameter, and we see a logarithmic divergence in lambda.
Yes, exactly. This was the equation I was talking about. Sorry, you didn't see it. So, right, so the total azimuthal angle that you accumulate as you go around, and this is kind of proportional to the number of photons that you observe, that your light ray picks up, is logarithmically divergent in delta rho and how far you are from the critical surface. And this dashed line here is exactly the surface that you saw enhanced in the image, the dashed line. And this line is kind of how you would see the horizon if you would have Newtonian gravity, if just the photons would come directly to you. This will be kind of the event horizon, rho equals 2m, the Schwarzschild radius. So the shadow is actually bigger because, as Ofik said, if you have light rays that come from very far away parallel, you can get kind of sucked in the black hole. So this makes the image seem larger than it really is. And this equation is just telling us that we can, in principle, invert this relation and get delta rho as a function of delta phi. What this is telling us is that in order to see, for example, an extra rotation of 2 pi, or an extra rotation of pi, let's say, okay, so an extra half turn around the black hole, we would need to go exponentially close to the critical surface. So delta rho would need to be e to the minus pi, which is about 1/20. So if we want to make another half turn around the black hole, we need to go to a distance from the critical surface, which is 1/20 about. So it's really like squishing all the images of something that went another half turn, squishing them exponentially close to the critical surface. Okay, and if we have another half turn, it's having it more exponentially close. And so you can kind of think of it as all the images get piled up here on the critical surface. They get thinner and thinner also, exponentially thinner. All right, good. So now do you see now the new slide?
Yeah.
Okay. So let's get some intuition into this. If you want to be very prosaic, you can say that near this critical surface, we get actually an infinite number of self-similar nested images of the whole universe. Okay, this is, of course, ideally. Why? Because you can, in basically every, of course, this is not very practically important, but every star in the universe, you can see an infinite number of images of that star near this critical surface, because a light ray from that star can go around the black hole and come back to you. And then you have an infinite family of light rays that does the same thing. And the images will appear at different points near but all of them will be very close to the critical surface. Okay, but let's think now, okay, so let's think of some emission very close to the black hole. Let's say some star. Maybe it's also a black hole by itself. Just a joke. Yeah, I mean, just any image here. Let's see what the image of it will be around the Schwarzschild black hole. So there's a Schwarzschild black hole somewhere here in the back, and that's its critical surface. So we will see one image of this star coming directly to our eyes. It may be weakly lensed a little bit, but it will basically come directly to our eyes. There will be another image of a light ray that goes around the black hole and comes from the other side. You'll see it's also mirrored, right? I mean, it comes from the back of the black hole, and it comes from here. But then there will be another image of a light ray that went one whole turn around the black hole and came from here. And then another one that went 1.5 turns and came from here. And as I said, all of them will be exponentially squished close to the critical surface. Okay. The same thing happens from the inside as well, actually, because in the inside, let's say I have some star in between me and the black hole. So I can see it. It just comes, a light ray can come from that star directly to my eyes. But then I have another light ray that went half a turn around the black hole and came from here. And then one that did a whole turn and came from here, etc., etc. So there are two families, infinite families of images that bunch up around the critical surface. And I can actually divide the sky into regions like this. So images in which I get, so rings in the image, in which I get images that went n times around the black hole. So in this region, I can get only things that came directly. In this region, I can get both direct and things that went one time. In this region, I can get things that went 2 times, etc., etc. And these rings come closer to the critical surface. Okay, so that's the Schwarzschild case. Now what happens in the Kerr geometry? So Kerr is it's still very, very simple metric, which depends only on 2 parameters, the mass and the spin of the black hole. And the spin is J here, and sometimes we parameterize it by A, sometimes we parameterize it by A, the spin parameter. Okay. And this is the Kerr metric. I just wanted to show it to you. That, I mean, it's a highly non-trivial solution of the Einstein equations with this spin and mass, but it's an exact solution. So we can, in principle, we can write it down in one line. On the other side, really understanding what's the behavior of geodesic, what's the behavior of stuff in this geometry is still a subject of active research. So it's really remarkable how the simplicity on one side, in contrast to the complexity on the other. These are the geodesic equations in Kerr. You can see that they're more complicated than in Schwarzschild. But for our purposes, the principle will be pretty much the same. There are enough conserved quantities to solve exactly for the motion. So we have a conserved energy omega, or if you can think of it as the frequency of the photon. There's a conserved angular momentum around the z-axis. That's where we have axial symmetry. And then we also have this parameter k, which is the Carter constant. That's a non-trivial conserved quantity, which is related to the polar motion in the direction where we naively think there is no symmetry. So we don't expect any conserved parameters naively, but still you do get conserved parameters because of some non-trivial property of the Kerr geometry. It's not the same case as in Schwarzschild, where we have conservation of angular momentum because of spherical symmetry. It's really a non-trivial property, and this discovered in the 70s by Carter. But the point is that there are enough conserved quantities to basically reduce the system to a first order form, like here. And then basically we can write, again, dr d sigma equals some square root of some potential. But now we will have also a similar equation for the polar motion. So the polar motion will be also some d theta d sigma. Theta is the polar angle, equals some polar potential. You don't need to notice the details too much, but just to appreciate that it's a highly, it's significantly more complicated problem, but still there are enough conserved parameters. And this down here, you can see the radial potential and the polar potential, this big R and big theta. Okay, but so because we have the same thing with the radial potential, then we will again have a critical surface, just like we had in Schwarzschild. But now the critical surface, photons can orbit an arbitrary number of times. It's not a circle anymore on the screen. That's broken because there is no symmetry there. So, but for mild spins, for example, 0.7, you can see this is the blue dashed line here. It pretty much looks like a circle still. Oh, and also this is from very close to the equatorial plane. So that's where I can see the asymmetry most pronounced. If I look from the polar axis, then I always see a circle. If I look from the equatorial plane, the symmetry is broken because there's a preferred direction of the spin. And then the shadow, this critical surface, is deformed, but it's deformed only for very high spins. For mild spins like 0.7, it's basically, you can only see a circle there. And the red dashed line is for spin 0.9999. Okay, very close to extremality. But there you can see a very interesting thing that maybe we'll comment on later. You can see this deformation, and there's a straight line appearing here at some angle. It's very strange. So, but the condition for this critical orbit is still the same condition. R equals R prime equals 0. This is what determines this critical surface of the image. And here we work in the space of impact parameters, or these are the angular momenta and Carter constant, square root of the Carter constant actually, but yeah, so normalized by the energy. So these are these lambda and Q. These are the impact parameter related to the z-axis, that's lambda. It's like the LZ, it's like the angular momentum around the z-axis, the spin axis. And Q is like the angular momentum in the rest, perpendicular to that. Is the angular momentum related to the motion outside the equatorial plane? So things in the equatorial plane, for example, have Q equals 0. Things that outside the equatorial plane have non-zero Q. And then they can kind of oscillate around the equatorial plane or do things. So one potential for measuring spin is if you can really look close to the equatorial plane, and if the black hole has high spin, then in principle, you could measure the deformation in the size. You could measure, for example, this length and compare it to this length, right? And if you can do this, you can say something about the spin. That would be very nice. One of the problems, I mean, it's a valid, I mean, well, so for mild spins, this is not a very strong effect. I think that, yeah, I think that for like spin 0.9, it's supposed to be like a 2% effect or something like that. But it still could be something that we could measure in the future if we had good resolution, good enough resolution. Currently, it's not within our reach. And also, the problem is that M87, black hole in M87, we're looking at it probably from 17 degrees. So from 17 degrees, it's basically a circle again. So that's a shame. If we somehow send someone to rotate the black hole or something.
So do we know the angle we are in relative to the central black hole in the Milky Way, Cygnus X1?
I don't think we know it. Yeah, I don't think we know it. I mean, of course, we're in the plane of the Milky Way, so we could maybe hope that we're closer to the equatorial plane. That would be great. But I don't think there's, but in the Milky Way, there's no jet. And so I don't think there's a consensus that like the black hole is like rotating with the same angular momentum direction as the galaxy. I don't think there's any indication for that. As far as I know, yeah, as far as I talk to people. Yeah. Yeah, but that would be interesting. So definitely, at least for high spin, it would be much more interesting to look at it from the equatorial plane. Okay, so let's see how these critical surfaces work in Kerr. So this is a diagram. So the thing is that in Kerr, it's not one photon shell. It's not one photon sphere. So in Schwarzschild, all the photons that go around the black hole many times are all this unstable critical orbit, form a sphere in the geometry. But in Kerr, it's not a sphere. We call it a photon shell because the sphere gets puffed up. You get these critical orbits actually in various different. I see that. Wait, we lost each other again. No.
I see all the changes on your screen. I mean, I see.
Ah, good.
Okay, now I see photon shell and ring.
Excellent. Okay. Good. So, so the photon shell is a generalization, if you want, to Kerr of this photon sphere. So in Schwarzschild, we would only get this white line here, which is a sphere around the black hole. But now in Kerr, we have these critical orbits at various different radii. So we have orbits that actually go around the black hole, but at many different radii. And what's different between these orbits is they also oscillate in the polar direction. So they kind of go around the black hole at various angles. This innermost one is the co-rotating critical orbit, the one that co-rotates with the black hole. And that's a circular orbit in the equatorial plane. This outermost one is a counter-rotating circular orbit, again, in the equatorial plane. But in between, we have also orbits that oscillate in the theta direction. Okay? Here, and here, and here, and they oscillate with different maximal angle. So it's kind of a more complicated structure, but you can still write it down analytically. And the images that you see down here are what you see when you look from different angles on the black hole. What the part of the photon shell, sorry, the photon ring. So we call, the photon ring is what we call what you see on the screen. And the photon shell is the region in the space-time. Okay, so this is the shell. And this is what you see on the image. So from up, you just see this one. Okay, so and sorry, and just to add another sentence, the very kind of counterintuitive but cool feature of this is that as you look on the screen and you look on the ring on the screen, you're looking at different angles here. In the geometry, you're actually looking at different radii. Okay, because every one of the photon, or every one of these orbits in the photon shell corresponds to a specific value of the angular momenta, which corresponds to a specific point on the screen. So if you're looking from down the barrel, just from the spin axis, you can see only one orbit, this orbit here. But if you're looking from 17 degrees, then you can already see a family of orbits in between these dashed lines. And if you're looking from the equatorial plane, then you can see actually all these orbits from here to here. But again, just to stress that as I look on different angles on the screen, I'm actually looking at different radii here in the photon shell. So this is what the colors are supposed to show. And yeah, let's see this. Very nice. Can you see this?
Yes.
Good. So let's, this is a really nice demo done by Leo Stein here that shows these critical photon orbits. So you can go and play with it on his website if you want. Kind of a nice way to see the photon orbit. So this is the spin. Let's crank it up to near extremality.
Can you put the link in the Shahar, put the link in the chat box so people can play around with it on their own computers now or later. Just because the
yeah, okay.
kind of low.
Yes. Good idea. Chat. Wait, how do I do this?
Is it just what's written on top? Duetosymmetry.com, or is there some sub?
No, it's just this. Charispherical photon orbits due to symmetry.
Okay, I think I have it. Okay, I can probably.
You have it? Okay, sorry. Yeah, thank you.
Okay,
okay, wonderful. So, yeah, that's a great idea. So, if we look at this, so you can play here with the different. So what I'm doing here is I'm tuning the spin to near maximal, and I'm playing with the different photon orbits. So you can see that I'm starting with the outermost orbit, which is a counter-rotating circular orbit in the equatorial plane. And then I'm starting to reduce the radius, and the orbit is starting to get out of the equatorial plane. And you can see the radius is decreasing, but the sphere is almost closing. At some point it will close exactly. That's where the lambda is equal to 0. The angular momentum around the z-axis is equal to 0. because only then the photon can actually reach the pole. And then it starts going away from the pole again. And I'm going to smaller and smaller radii. And these come closer and closer to the horizon. This is a black hole which is very, very strongly rotating, 0.999. And you can see that they all kind of get stuck to the event horizon in the end and go in the end to a co-rotating circular orbit. So that's kind of a depiction of all these orbits. So it's a much nicer, much more interesting structure than you get in Schwarzschild. Wait. Wait, can you see my presentation now?
I see critical orbits photon shell.
Okay, good. Why am I not seeing this on my screen? I don't know, but okay. Oh, good. Okay, I will just continue. Okay, good. So, can you see? It's annoying me. 1 second.
If you can, okay. Large winding limit.
Okay. Yeah, for some reason, I'm not seeing this on my screen, on my computer screen, but that's not very important. Okay. So we can do a calculation in Kerr, which is very similar to the calculation that I showed you in Schwarzschild, of this, how the brightness diverges near the critical surface. Again, it works basically the same, but it's more interesting because, I mean, you don't need to follow all the details here. The thing is that the geodesic equation in Kerr, one of the equations that's derived from it is this equation here. And the radial potential has, again, a double zero near the critical surface. So it gives a logarithmic divergence. And this angular potential gives the number of turns times a finite number, which depends on which orbit in the photon sphere we are in. So, right, so, but the thing is that this logarithmic divergence comes now with a coefficient. This coefficient depends on which orbit in the photon sphere we are in. Depends on this R gamma, which radius in the photon sphere we're in. Remember, we said there's a family of orbits there. And this is the parameter. This is basically the second derivative of the radial potential at the critical, at the top of the potential. And this is exactly the Lyapunov exponent that Ofik was referring to. It's R double prime. So what we get from this is that the brightness diverges, again, logarithmically near the critical surface. Can you see now a new slide, angle-dependent divergence? Okay, yes. So I is the intensity on the image, and which is proportional to the number of times we orbit. N, actually, it's the number of half orbits here, okay? Because it can come from down, it can come from up. So it's proportional to this N, and it's logarithmically divergence with delta rho, just like in Schwarzschild. But now it has a coefficient, 1 over gamma, and gamma is this Lyapunov exponent, which is roughly just the second derivative of the radial potential. Okay, this is, you can think of it as, you know, a measure of how much the potential, this potential that we had, how much it's curved near the critical point, which tells us how fast, if we have something in top of the potential, how fast it will want to go away from the top of the potential. If it's very flat there, it will go slowly. If it's very sharp, it will go fast. That's what the Lyapunov exponent characterizes, how unstable this orbit is. Okay, so this is just to emphasize, this is again a feature which is only depends on the geometry, only depends on M and J of the curved geometry. Okay, and again, you can invert this relation. Oops. Again, you can invert this relation. Again, you can write that delta rho n is e to the minus gamma n. So I just want to emphasize again that as you go along the ring on the screen, this gamma will have a different value at every point on the screen. So it's really a function of r gamma, which is a function of the angle we are on the screen. So at different points on the screen, we have different Lyapunov exponent. Okay. And this Lyapunov exponent characterizes how exponentially close everything will be to the critical surface, right? If you have, like, the second image is e to the minus gamma closer to the critical surface than the first image, etc., etc., etc. Okay, so what will we have in a realistic scenario? Sorry, I'll just take a few more minutes, if that's okay. I'll try to.
How many do you need?
Well, between 5 and 10, you tell me.
Okay. That's okay.
Okay, good, thanks. So, right, so the self-similar structure of the image. So if we have an accretion disk, which is now, let's say we have a scenario of a realistic accretion disk that is kind of, it's peaked at some radius away from the black hole. This is kind of a view from above. And will be a view from the side. So the accretion disk kind of fills up, is more peaked near the equatorial plane, but less peaked near the poles. Okay, and it's peaked at some radius away from the black holes. Pretty realistic scenario for an accretion disk. We don't really know what's going on in the accretion disk itself, but it's roughly of this form. So what we claim is that you will see a repeated lensing of this emission region, and it will yield a series of demagnified images or subrings. Okay, so we'll see this accretion disk again and again and again and again and again in the image an infinite number of times. All these images will be exponentially close to the critical surface and exponentially demagnified. So it will be squished kind of very close to the photon to the critical surface. And this is an equation that describes it. The n+1 ring is exactly the nth ring, but it's squished. It's squished because of this factor e to the gamma. Okay, that's the thing. And the thing is, again, the squishing of the image is different at every angle. At every angle, you have a different gamma on the image. So this is a thing that you can, in principle, measure. Okay, and this is, again, you can see simulations. This is actually the GRMHD simulations and the ray tracing, and you can actually look at them and see this formula. So these are, this is the brightnesses. These are the contributions. We could separate it into contributions of photons that went zero. Oops. Sorry, photons that went. So this is kind of the image. You cut it along some axis like this or like this. This is the red and blue colors. And then you can zoom in near one of the peaks, and you can see that it's actually composed of this series of repeated images. So these are the zoom in on the peaks of this plot. So you can see there's an n equals 0 contribution, and n equals 1, on top of it an n equals 2, n equals 3, and each of them is exponentially demagnified and closer to the critical surface, which is exactly here. This will be the rho critical. Okay. And the thing is that the important thing is that the form of this, the profile of this emission, that's not universal. That depends really on the details of the accretion disk. But the fact that it is the same profile that's lensed according to this equation, just squished by a factor of e to the gamma, that's universal. And here is the statement, okay, here is the statement that the flux in the n+1, so because they're very squished, their brightness is larger, but their area is exponentially smaller. So the flux in the rings is exponentially small. E to the minus, the flux in the n+1 ring is the flux in the nth ring times e to the minus gamma. So this is a bit worrying, right? In the beginning, we were a bit worried. Okay, so this is a very nice story, but can you actually see this? I mean, the flux is exponentially small. Can you see this? Looks very weird, right? So that's can you see the new slide? Total flux and subrings negligible? Okay.
Yes.
Are they measurable? And this is, I think, the really cool part here, that we think the answer is yes. Not today, but they will be not very, I mean, the measurability can be not so far away, we think. Thing is that, okay, how is this image generated? This is a very interesting story in itself. I won't have time to go into much detail, but it's generated, it's not a usual telescope, right? I mean, it's generated using very long baseline interferometry, VLBI. And these are an array of radio telescopes that measure actually the electric field that emitted from that region as a function of time. And then you use correlations between pairs of telescopes. You correlate the signal E of t at one point with another signal E of t at another point. You do a correlation between the two. And this turns out to give you, after a calculation, a Fourier component of the image. So actually, what these guys are measuring is exactly the Fourier components of the image. So actually, it's more natural for them to work in Fourier space. Right? So every component it's a 2D Fourier image of the 2D Fourier transform of this 2D image. Right. And the thing is that the K, right? So if we do a 2D Fourier transform, we have a K, which is the wave number of the different, the different parts that we're adding. And this K is proportional to two things. One is the wavelengths. So going to higher wavelength can increase your resolution. So going to higher K means increased resolution. But kind of surprisingly, going to longer baselines, larger separations between the telescopes also increases your resolution. So that's why the telescopes are spread over the whole Earth. Currently, the effective size of this lens, of this telescope, is the whole Earth. But if we will send a satellite or put another telescope, another dish, another radio dish far away from the Earth, I mean, we can go to higher frequencies. The problem is that higher frequencies, there's a problem with absorption in the atmosphere. It's really like, it's really kind of, now is the maximal, it's a maximal frequency that can be achieved because of the absorption of the higher wavelengths in the atmosphere. But if we can send something very far away, that can increase our resolution. So this is kind of, this is not measurements, but this is kind of a plot that tries to show what we can achieve if we both increase frequency and send satellites far away from the Earth. So you can see that the current, so this is the visibility amplitude of the Fourier transform of the image. And these are Fourier transforms of annuli corresponding to the different rings. So it's just annuli with exponentially diminishing widths, corresponding to n equals 1, n equals 2, n equals 3.
If you're writing something, I don't see any. I don't see. Do
you see the measuring subrings?
I'm still on the very long baseline interferometry page.
I see. Okay, sorry, we're very close to the end.
Okay, now I see measuring subrings.
Good.
And now the extremal limit.
Okay, so right. Okay, good. Now you see measuring subrings again?
Yes.
Okay, So this is the Fourier transform of annuli corresponding to the different rings. We model just the rings as some annuli at, kind of fixed diameter, but in diminishing widths, like the rings that I described to you. This is the black is n equals 1, the red is n equals 2, the blue is n equals 3. The thing is that you can see that even though the flux is diminishing exponentially, when you go to very large baselines, it turns out that if you go, because it's very large baseline, you're more sensitive to very sharp features on the image. Okay, even though the flux in them is very small, just the fact that they're very sharp in the image makes them dominate at some very large baseline. So actually, if we go to the moon, for example, we think that we can see the n equals 2 ring. And if we go to L2, the Lagrange point, we can see maybe the n equals 3. Okay, but and these guys here are satellites in low Earth orbits, middle Earth orbits, etc. The current EHT resolution is this. You see, there's still a lot to improve. The current EHT resolution is this, and the fact that in the Fourier transform you see this first dip is exactly the fact that you see a shadow, because the Fourier transform of an annulus, the radial part of it, is a Bessel function, and this is the first zero of the Bessel function. That's the shadow. The fact that actually the Event Horizon Telescope, the people, what makes them really convinced that they really saw shadow is not the image that they generated for PR purposes, but it's the fact that they see a dip in the Fourier transform, a very strong dip. So this means that it's really an annulus, and not some Gaussian or something. Yeah, so this is kind of prospects for the future, and yeah, we think that if you send the satellite far away from the Earth, we can actually maybe see the subrings, hope to see them. Yeah, I wanted to tell you some more things about the extremal limit, but I think I'll defer to, I'm happy to tell you about it at some time. I want to, we can leave it, I don't know, for the questions. There's some very interesting story about this shadow and the extremal limit with cool features. And this is the picture from Interstellar. Yeah, so, and we're also doing some more theoretical work, trying to understand really the symmetry structure, these photon rings. I think there's some prospects for the future. So there's some, I'm pretty excited by this thing. I think it's kind of very new. It has, it's a new way to look at black holes, which is kind of complementary to the gravitational waves way to look. Of course, the gravitational waves way to look at the black hole still has the big advantage that it's actually looking at dynamical processes of black hole collisions, neutron star collision. It's still looking at the, these processes which are dynamical, which is a very big advantage. But I think this is, an orthogonal way to look at black holes, which is you can actually learn a lot about the stationary metric of a black hole from that. And I think it's really interesting.
I'll just say from the gravitational wave side that since gravitational waves are basically massless, they would follow the same geodesics and null orbits that you're describing. So everything you presented here is relevant for gravitational waves as well. Right.
Yeah, I agree. Right, but here, kind of the advantage is that the electromagnetic emission near black holes is very strong. Yeah. Right, and it's also different frequencies. For example, the gravitational waves, you see, like the frequencies are the frequencies of the orbit, and here we're looking at frequencies which are frequencies of the photons. It's very complementary. It's very like two different regimes, and right. So there are many interesting things for the future. Looking at time-dependent signals, observing the accretion physics and the jets, understanding better the theoretical symmetry behind this equation that I showed you behind this kind of self-similarity of the image. Trying to find candidates for high spin or for some new physics. Yeah, so I think thank you for staying. Yeah, I think this story is a rich and nice story. It's kind of reminiscent of critical systems, this near critical analysis. It's nice from the theoretical point of view. It's very nice from the experimental point of view. We can actually look at black holes for the first time, like look optically. And hopefully it can be observed, the photon ring. And yeah, that's what I wanted to say. Thank you.
Thank you very much, Shahar. And if anyone else has any questions. You're getting silent applause from Max here in the back.
Oh, yeah. I'm sorry for going over time.
I feel none of us have yet calibrated timing to technical difficulties over these new platforms.
Right. Okay. Yeah, I have the benefit of that.
Okay. Questions again, going once, going twice.
All right.
Okay, thank you, Shahar, very much. Thank you all for coming. We have another seminar same time next week.
Thank you.
And have a great semester, everyone, and good health to all of you and your families.
Thank you.
Thank you very much.
Thank you.